Hi everyone. So this is going to be the video lecture that we missed on Wednesday because of my power outage at my apartment complex. So what I've decided to do instead of trying to cram a lot in from a lecture where I can't get a lot of feedback from, so my 10 a.m. class did get ahead of my 11 a.m. class. So my goal is for this lecture is anyone from the 11 a.m. class, this should be a pretty short lecture. We're just trying to get through where my 10 a.m. class got to. I wouldn't say there's not a little, but we can definitely get through the majority of the rest of chapter 17 on Friday. It's pretty straightforward. Again, it's more ice tables, so I think we're in good shape. So effectively what this is a lecture to catch up my 11 a.m. class to my 10 a.m. class. So I'll do my best to make this succinct, and that's the way we're going to go forward from there. So for my 11 a.m. class, we left off talking about the last type of titration that I said we'd talk about, right? We've already looked at strong acid, strong base. We've looked at weak acid, strong base. And the last titration I said we'd look at is going to be weak base, strong acid. So if we look at a representative example, we have ammonia. Ammonia will be our weak base. Strong acids, right? I've already gone ahead and simplified this. So strong acids could be, and I've given you the list, right? It could be either hydrochloric acid, nitric acid, sulfuric acid, hypochloric acid, something like that. When added to water, they effectively 100% dissociate into hydronium. So for us, I'll keep it generic and use H3O plus as our strong acid to represent any of our strong acids. Just like what we said when we were dealing with other titrations or other neutralization reactions, if we have strong acid or strong base, I don't care, as long as we have one, and we got one, we're saying that neutralization reaction is so strong, the K is so large, everything will be converted into products. So what that's telling me is that I'm going to form ammonium and water. So what is this going to look like when I titrate, though? Remember, titrating means I'm taking a known or an unknown amount of, say, in this case, I guess, an acid, and I'm titrating in a known amount of acid. Did I say that correctly? Let me just make sure I back up. Right, I have an unknown amount of base, right, NH3, and I'm titrating in a known amount of acid. So let's go through the same steps that we've done before, right? So we have a 0.1 molar solution of ammonia. We know ammonia is a weak base. You predict that the pH would be above 7 when no acid has been added. Well, the pH is well above 7. We're in good shape. We start titrating small amounts of acid in. Well, what's happening when that happens, right? So we start with ammonia. We're titrating in small amounts of acid, strong acid, so we know it's going to be hydronium. I know I drew it weirdly because I'm going it down. I'm trying to deal with the space that I have, but that's going to form ammonium, and that hydronium converts into water. And so that's the process that I'm looking at. So as more and more of the acid is titrated in, more and more of that ammonia, which is basic, is being converted into ammonium, which is slightly acidic in water. So you would predict a small decrease in pH. And it's exactly what we see. Eventually, oops, let me go back to the highlighter, right? Eventually, we titrate in enough strong acid that there's a good amount of my weak base, there's a good amount of my weak acid. They're conjugate to each other. That's my definition of a buffer. And so actually in the center of, again, of the shaded area, I have a buffer. That means if I add a strong base, it gets converted into a weak base, so a mild change in pH. If I put in a strong acid, it's converted into a weak acid, just exactly like what I have on the screen, so a small change in pH. So you're buffering that region. And just like what we saw before, it's only good for about plus or minus 1 pH unit from the pKa. And we've also shown, using the Henderson-Hasselbalch equation, when the conjugate base and the conjugate acid are in equal amounts, right? When they're 1-to-1 molar ratio, pH equals pKa, half equivalence point. That's the strongest buffer. It's exactly what we see. The only difference is, right, if we want to put it into perspective, right, this is why for biochemists and for biologists, buffers matter so much. So when we're looking at the acetate buffer, right, that buffer between 6 and 4 pH, other than outside those ranges, it broke. If I cared about buffering a reaction between, say, 8 and 10, well, then I would use an ammonia buffer, right? So it does matter when running experiments, even these little things, to control what's happening, right? So long story short, right, we have our buffer zone. Once I titrate in enough acid, right, I can break that buffer. What does breaking mean? I've added either too much acid or too much base. Well, in this case, I have way too much ammonium. The ratio from ammonium to ammonia is too small. The buffer doesn't work. And what I see is as soon as I add acid, it just plummets, right? At a certain point, I'll have exactly the same amount of, let me clear everything. Oops, I didn't want to clear that much, but I can write it again. I'm going to have exactly the same amount as ammonia and ammonium, ammonia and hydronium, that when that reaction is over, the only thing I have left is ammonium and water. Well, if I have ammonium and water, ammonium is a weak base, a weak acid. We've already gone through this in last week or on Monday's lecture. And we said, well, you would predict it to be less than 7. You have a weak acid with water. And look what happens. There's our equivalence point. We've already predicted it. It's below 7. We're in good shape, right? So we keep titrating. Once we've gone beyond the amount of ammonia we have, effectively all I'm doing is adding more acid to the water, and you get that rapid drop in pH. So you get that S-shaped curve. And that's what we're looking for when we're talking about titrating a weak base with a strong acid, right? Effectively, it's a mirror image of what we did when we're talking about a strong acid, weak base titration. Oh, sorry, vice versa. Strong base, weak acid. So these next couple of slides are just kind of walking through slowly what I've already said. And the last thing that I want to cover in this is just polyprotic acids. Polyprotic, right, means we have multiple acidic protons. So more than one proton that could be donated to a Lewis base, basically making it an acid twice over, right? So there's 2 H's that can be transferred. So there's a lot going on with this slide. Let's go through it slowly, right? Just like we would predict. We're taking a acid and we're titrating in a base. So low pH, makes sense. Titrate, titrate, titrate. I hit basically my influx in that curve. Well, I have my equivalence point. I know exactly the first point in which all of that first acidic hydrogen is gone. Everything left over now is SO4 minus. And so if we stopped here, we still see that S-shaped curve, right? But if I keep titrating to the next equivalence point, what I'm looking at is what happens when that second acidic proton is, or that molecule of HSO4 minus is converted into SO4 minus. And then after that, there's no more acidic protons. It just becomes more basic as I titrate in more OH. So a couple of things we can pull out of this. First off, right, we already talked about our first equivalence point, nothing new. The new thing might be our second equivalence point, right? We're talking about one H and then a second H. One is the first, the more acidic proton. The second is the less acidic proton. Other things we can pull out of this graph will be the pKa's. And we've already gone over this once, right? We did this with the Henderson-Hasselbalch equation. We're saying what happens when the amount of base and its conjugate acid, or acid and its conjugate base, are equal, right? The ratio of 1 to 1, the log of 1 is 0, so pH equals pKa. What we've done in a single experiment has been we've found the equivalence point of both the H2SO4, I'm assuming that everything's H2SO4, right? We found the first equivalence point. We found the second equivalence point. We found pKa1 and pKa2. From one experiment, we've gathered a tremendous amount of data. So being a smart scientist, you can pull out a lot from very simple experiments. And I think this is why it's a really good example of why acid-base chemistry is so very powerful, right? We pulled out a tremendous amount of information. In real life, you'd probably do this 3 more times and average everything together. But the idea is you've pulled out a lot of information because you smartly designed an experiment. All right, I'm going to leave it at that. We're going to pick up after this tomorrow on Friday. So I hope that was a good catch up for anyone from the 10 a.m. class, and I hope that was a good lecture for anyone who is from the 11 a.m. class. So again, I will see you all tomorrow, and